Okay, we're continuing with Chapter 10 in the statistics textbook. In this video, we're going to be going through Section 4, which is on the regression fallacy. Okay, so if you read through this section for the first time, it can be a little bit confusing. And the reason why is, the regression fallacy is based on what's known as the regression effect. And if you do a Google search or YouTube search on the regression effect, this is something that I think all of us are inherently familiar with. It's the idea that if you've got an existing set of data on something with, a good number of data points underlying it, then for any future data points, there's like a gravitational pull towards the average. So if for example, if somebody, a professional baseball player has a batting average of 310, and this is built up over 5 years of playing, and it's just this person's been this consistent type of hitter year in and year out. Nothing's really changing. And so the sixth season comes and they're playing, and it's like all things being equal. And, in the middle of the summer, he goes on a hitting streak for a couple of weeks, 2-3 weeks, and he's batting 390 during those weeks. Well, in upcoming at bats, we're going to expect that relative to the previous 3 weeks, he's going to start hitting worse. Like he won't do bad, but one day he'll hit 1 for 4. Then maybe the next day he goes 0 for 4. Then maybe the next day he goes 2 for 5. So it's worse than the previous 3 weeks. Okay, and that's the regression effect, and the regression fallacy is just the idea of you attribute the fact that he's hitting worse, relatively worse, to something related to baseball. Oh, the crowd's been heckling him or something, and he's gone on the road. He's been tired. That's why he's hitting worse. When in reality, he was gonna that was what was gonna naturally happen no matter what. His batting average is 310, 320. He's just been hitting, doing well of late. But he's a 310, 320 hitter. It's just the statistics. There's no actual physical explanation for it. There's no deeper analysis of what's happening. It's just the regression effect. Now, again, we're kind of assuming that there's no extraneous confounding variables at play, that he didn't change something with his swing, or if it's a young hitters will mature and get better and better. So maybe the guy's getting better, but just in general, with no confounding variables, that's the idea of the regression effect. And again, a regression fallacy is you're coming up with some conclusion for something that's just purely statistical. Nothing's changed. It's how he naturally is as a hitter. It's just for some, and yeah. So now, but why did he all of a sudden hit better? What's the explanation for that? What was happening that caused him to hit better for those 3 weeks? Or it could have been he hit worse. So when it comes to the regression effect, we look at these deviations from the average as just chance error. Now, there's obviously, technically something going on, but we can't as humans, figure it out. But that's just how statistics are. That's how things in life happen. You've got everything's right around the average, but where the variations are coming from, we can't say. If you're on if you have a team in football, they year in and year out, they go 8-8, 9-8 every year. It's like that same type of team. Well, if they're on a little bit of a win streak, then we're going to be expecting them to lose. Now, why are they on the win streak? Well, okay, if you watch some of these games, there's just tip balls go their way at the right moments, or just they're pretty good. They call good plays, and just the defense was. They were playing against teams that they were matched up well with, and now they're switching to teams that they aren't matched up well with, or just they called some right plays at the right time, and it's just that chance variation. But at the end of the day, it's like Bill Parcells says, you are what your record says you are, type thing. And if their record is year in and year out, the team doesn't change, it's always 8-8, 9-8, then that's the kind of team they are. Doesn't matter what it looks like at a certain moment. Okay, so yeah, we want to keep in mind that it's the regression effect is that gravitational pull towards the average, But why are you deviating from the average to begin with? It's like chance. I don't want to say error, but chance variation. You could say chance error, but I mean, it depends on what it was. So like, was it an error that the batting average was higher for 3 weeks? I don't call it, you call it an error. But okay, so yeah, that's the regression effect. So why is this section a little bit confusing then? What's so confusing about that? Well, because we're going to be looking at the regression effect from a little bit different of a perspective. What we're doing in this section is we're looking at how the regression effect manifests itself in relation to a 2D scatter plot, and in particular with a football-shaped data point cloud or elliptical shape. We're going to see it's the regression effect that this is what causes the regression line to deviate from the standard deviation line. It's the regression effect that causes what we saw in the previous section about the when it comes to a percentile. If you were in a higher percentile, above average percentile, so above the 50th percentile, and for the incoming variable, the input variable, then on average you're going to be in a lower percentile for the output variable. This is for any football-shaped, like linear type scatter plot. No matter what it is, 100%. It doesn't matter what the study is about. If you have a football-shaped cloud, so it's like that linear correlation coefficient is applicable, then that's 100% going to be the case. That if you the incoming data point, you're in a higher percentile, above average percentile, above 50%. Like if you're in the 67th percentile, then on average for the outcoming data point, you're going to be in like the 62nd percentile on average. On average, doesn't mean that like there's exceptions that are be above average percentile both, or like they'll start in the 67th percentile and then go to like the 72nd. Yeah, some data points, but on average it's going to be lower, and vice versa. If you're in a lower percentile, the lower than average, so like the 37th percentile for the incoming variable, then on average you're going to be in like for the outcoming variable like a 43rd percentile. Okay, so now before we get into this, just note that in this section we're really going to be focusing on scatter plots with the football elliptical shaped data sets to see how the regression effect manifests itself in these types of scatter plots. But in general, these concepts are going to extend to any kind of scatter plot, even like a quadratic shaped scatter plot. Now, how exactly the regression effect manifests itself, there could be some different specifics for a different kind of scatter plot, again, in terms of how exactly the whole regression effect manifests itself, but the same general concepts are going to be there. Like a gravitational pull towards it's really, you think about the point of averages. So you've got, there's a gravitational pull. Here we've got with the batting averages, we were talking about a single data set, gravitational pull towards the batting average. But here we've got two data sets, right? So it's like a gravitational pull in the X direction toward the average and in the Y direction. And you could kind of think about that as it's a gravitational pull towards the regression line. So yeah, just as we go through this, again, we're going to be focusing on the football-shaped scatter plot, but these same principles are going to be the same with any kind of scatter plot. But there might be some subtle nuances here and there about how everything plays out with another type of scatter plot. Okay, so it says a preschool program tries to boost children's IQs. Children are tested when they enter the program, the pretest, and again when they leave, the post-test. On both occasions, the scores average out to nearly 100, and the standard deviation is about 15. The program seems to have no effect. A closer look at the data, however, shows something very surprising. The children who were below average on the pretest had an average gain of about 5 IQ points at the post-test. Conversely, those children who were above average on the pretest had an average loss of about 5 points. What does this prove? Does the program operate to equalize intelligence? Perhaps when the brighter children play with the duller ones, the difference between the two groups tends to be diminished. Is this desirable or undesirable? These speculations may be interesting, but the sad fact is that nothing much is going on, good or bad. Here is why. The children cannot be expected to score exactly the same on the two tests. There will be differences between the two scores. Nobody would think these differences mattered or needed any explanation. but they make the scatter diagram for the test score spread out around the SD line into that familiar football-shaped cloud. The spread around the line makes the bottom group come up and the top group come down. There's nothing else to it. Okay. So we're dealing with a football-shaped cloud, and you can think about the football-shaped cloud. Yes, it's associated with that linear correlation coefficient, but it's not really there's going to be a lot of real-life circumstances that are going to have that football-shaped cloud. And I hesitate to say linear because, when you have R equals 0.2, I mean, it's not really much of a clustering around a line, right? So it's not really that linear, but it's still, even though it's not technically linear, this is still a football-shaped cloud is still going to be common for a lot of circumstances in life. So it's really more than just linear. Don't think about this as purely linear, because this a circular data set, the linear correlation coefficient is 0, but this is still applicable. The linear correlation coefficient applies 100% to this, right? Even though this is not linear at all, there's no correlation. Okay, but here they demonstrate the regression effect, specifically how it manifests itself with a football-shaped cloud. And so just note that a lot of the examples we're going to look at in this section, they're going to give to where the X data set and the Y data set have the same standard deviation. And the only reason they're doing that is because it allows them to present data points that are in like the units of like IQ points and whatnot. But what's really going on, we could look at this from a more general perspective. If the standard deviations of and the averages of the two data sets were different, it's manifesting itself when you look at the percentile rank. It's that the percentile rank is going to be, you're always, if you took any scatter plot, football-shaped scatter plot, and you analyzed, no matter what it is, and you analyzed, okay, you could always make an argument, no matter what, that, oh, look, on average, the percentile rank went down if you started above average, and it went up if you came in below average. And then that will always 100% be the case, no matter what. But when you have different averages and standard deviations of the two data sets, sometimes it's hard to show that in terms of not percentile rank, but like the actual units of the, like, here's IQ score. Okay, and so what they're saying is that you could come up with some conclusion. Look, perhaps when the brighter children play with the duller ones, the difference between the two groups tends to be diminished, right? But no, that's incorrect, because no matter what the data, it's obviously incorrect, because if it's a football-shaped scatter plot, you're going to see this percentile discrepancy, not discrepancy, but this pattern, no matter what. So it can't have anything to do with what's inherently going on. Okay, so it says, in virtually all test-retest situations, the bottom group on the first test will on average show some improvement on the second test, and the top group will on average fall back. This is the regression effect. So they're saying test-retest, but they're just trying to give an example of a typical football-shaped cloud example. But this is with test and retest, that's okay, incoming variable, outcoming variable. If it's a football-shaped cloud, then you're going to see the bottom group on the first test will on average show some improvement. You're going to always see, if you're in a lower than average percentile on the incoming variable, on average you're going to be in a higher percentile on the outgoing variable, and vice versa for all football-shaped clouds. Now, again, just want to make this clear. If we had a cloud that was like this, the regression effect will still be present, and it will result in some pattern for every single data set that's distributed like this. But exactly what that pattern is, like how the percentile ranks, what they exactly do, is going to be different than what we're seeing here. It's not like there's going to be, okay, this pattern is, if you're below average percentile, you're going to be above average percentile on the outgoing, and vice versa. That's football-shaped clouds. This is going to have its own unique way the regression effect manifests itself for every single data set that looks like this. And a regression fallacy would be that you whatever that pattern is, maybe you always see percentile ranks stay the same when you're at the top or something like that, and you're attributing that to something that's just a pure statistical manifestation. It's a pure that it comes from that gravitational pull towards the regression line. So Like you might be thinking, well, no, but that's a real pattern though. That's a real that's like this would be logarithmic. That's a logarithmic effect. So it is a real effect. No, it's like, okay, if you have a certain test that a teacher's giving, okay, and you have people that scored in the higher that got high scores on the test. Yeah, you have some people that are doing really well. That's true. And so on the next test, they'll do even better. But what naturally happens on tests when people do well? Well, a lot of times it's just you were just happen to be prepared for certain questions, or you just circled some multiple choice answers and you guessed right. So on average, if you scored higher, you're going to score a little bit lower. You're going to get pulled down towards the average. That's what's on average going to happen. Right? The teacher designed the test to be this hard, to be on average an 85%, everyone an 85B. That's how hard the test is. That's the way the teacher designed it. So if you have a bunch of people that made it from a 92 to a 97, okay, well, some might score higher on the second test, but on the average, it was just that chance variation. People were guessing right. They happened to study for that specific question or a couple of the specific questions that were given on the test. So on the next test, that's how it works, right? You're gonna all of a sudden you don't get the most desirable questions, or you don't guess right, and you get pulled back down towards the 85. It's that gravitational pull towards the average, and that's it. There's nothing else to it. So thinking that the regression effect must be due to something important, not just the spread around the line, is the regression fallacy, right? So what they're saying here is that there's a natural spread around the average due to, again, some people were on a test, people guessed right, people were prepared for certain questions that because some people don't study as much as they should. They just study bits and pieces. Well, they happen to guess right and study the right questions, but then on the next test they still study the same amount and they don't guess right and they don't get the best questions, so the grade comes down. It's that chance variation. So here's another good example to think about this. So again, here they give an example, and here we're looking at. So I just want to make this clear again. We're studying how the regression effect manifests itself with a football-shaped cloud. So you've got at on the x-axis is father's heights, and on the y-axis is son's heights. Okay, now you've got this elliptical shaped cloud. Okay, now, so the average height of the fathers is 68 inches. The average height of the sons is 69 inches. And they make the standard deviations the same in this case. Oh, yeah, R is about 0.5. They make the standard deviations the same in this case because it makes it easier to illustrate that. So, okay, the SD line, we've got... So here's the outline of this. The SD line runs right down the center, okay? And so if you're thinking about from the regression standpoint, how to predict the output variable given the input variable, your first instinct is to use the SD line in the sense that, so since the standard deviations are the same, we can say, okay, If a father comes in that's 6'6" tall, so that's what? That's 78 inches tall. That's a good bit taller than average. And now we want to predict what his son's height is going to be. Well, okay, on average, the sons were 1 inch taller than the fathers. So okay, we'll predict it's going to be 6'7", 78 inches tall. That's what what you would say if you're using the standard deviation line. Now, if the standard deviations were different, you'd have to look at it through, okay, if the father is this many standard deviations above average, then the son's also going to be that same many standard deviations above average. You couldn't say it like just 1 inch taller, but that they're doing this, they're making the standard deviations the same, so we can look at it that way. That okay, if the father is 77 inches tall, 6'6", then since on average the sons are 1 inch taller than the fathers, we're going to predict that the son is 78 inches tall. Okay, but when you think about it, we know intuitively that's not correct. This makes sense. this makes sense. Once the son reaches full maturity, so they're 30 years old, let's say, so they're fully grown, then on average, a son's going to be like 1 inch taller than his dad. That makes sense. That makes sense. However, for a certain special case where you have like a Michael Jordan who's 6'6" tall. Now we think about his sons. Okay, he's a professional basketball player. He's 6'6". He's got this athletic, tall genes. So yeah, his sons are going to be taller for sure. He's going to probably have a son that can go play in the NBA, definitely. Right? There is genetics at play for sure. However, it's still, we know intuitively that if Michael Jordan has 5 sons, I mean, yeah, you might have one that's taller than him, maybe 2, but like, no, I mean, you're going to have, in general, you're going to have, one's going to be 5'10", one might be 6'3", one might be, 5'9". I don't know. And what they say is that for the case of the 73-inch or the 72-inch tall father should have a 73-inch son, but in actuality, on average, it's 71 inches. So the case they look at here is you have a 72-inch tall father. We would guess that his son's going to be 73 inches tall, but on average, what you see, the scatter plot says that for a 72-inch tall father, the son's going to, on average, be 71 inches tall. That's where the regression line is going to go through. That makes sense. We would expect Michael Jordan's sons to be at least on average 2 inches shorter. So 75 inches. And that would be, to me, that's a little high. Right? There's no way there's no way Michael Jordan's sons are going to, on average, be an inch taller than him, all 6'7". There's no way. But why do we know that? Why do we know that? What's the reason why our instinct tells us that that's true? Because we go outside, we see people, we see grown men all the time in New York in crowds. Grown men on average are like 5'9", grown American men. Or okay, they say black people are more athletic. Okay, but you see black grown men, they're not all walking around where it's like, man, on average they're like 6'6". No, it's like 5'9", 5'10". So that's how we know. It's that gravitational pull towards the average. Michael Jordan is an unusually tall man, right? And so because of that, it's not going to just obey what's exactly happening at the point of averages because there's that gravitational pull. And that's what the SD line is not taking into account. The SD line is just saying, look, on average, a son is 1 inch taller than his father. So no matter where we are in the cloud here, that's what we're going to predict. But that's not correct, though. Now, why was Michael Jordan 6'6" tall, 77 inches tall? It's that random variation, right? Even though men, on average, grown men are 5'9", 5'10", we know that there's a spread around that. You can't have men that are 6'6". You can't have, there's unbelievably rare cases where men are over 7 feet tall, right? It's that random variation, chance variation. That's where the R is equal to 0.5 is coming from. But the standard deviation doesn't take that into, the SD line doesn't take that into account. The slope of the SD line is just sigma y over sigma x, but the slope of the regression line is R sigma y over sigma x. It's taking into account that variation. And so it's going to be, still go through the point of averages, but just be shallower. Okay, and so we're mainly looking at this right now from the perspective of x is the input variable and y is the output variable, but it would be the same idea if you looked at it like y is the input and x is the output. You'd just be looking at it from the other direction. There would be a pull towards that in this direction. But we'll talk about in the next section. We'll talk about the regression lines that where you look at y as the input and x is the output. For this case, there's not really a gravitational pull towards in this direction because we're picking the x variable. We're saying, okay, look, here's a Michael Jordan, right? There's no gravitational pull. We're that's the input. We're picking that height. Okay, so in these next 4 paragraphs here, we're not going to read through these. They're just talking about what I just described. The fact that we would expect based on just a pure standard deviation line, okay, on average, a son is 1 inch taller than his father. we would maybe guess, okay, Michael Jordan's sons are going to be on average 1 inch taller, but that's not true. Okay. Now, again, before we move on, I just want to make it clear that it's this whole gravitational pull idea is going to be present in a scatter plot that's not football shaped, something that doesn't correspond to the linear correlation coefficient. It's going to be present, and it's going to manifest itself in some way, but exactly how it manifests itself, the exact results are going to be unique to each type of scatter plot. Oh, and then, but you can see how the percentile rank comes into play. You picked Michael Jordan. He's in a higher percentile rank. Michael Jordan's in the input, he's in the 85th percentile, taller than 85% of men on Earth, right? Well, on average, the output, which is the sun's height, is going to be in a lower percentile. They're going to be taller. It's not saying that, it's not saying that, okay, well, Michael Jordan's sons aren't going to be on average taller. No, of course they are. It's Michael Jordan's sons. They're getting his athletic genes, his tall genes. 100% they are. We see that all the time, right? These great athletes, their kids are also great athletes. LeBron's son is in the NBA, right? Of course, that's true. So no, we are not expecting that on average Michael Jordan's sons are going to go below the average. Michael Jordan's in the 85th percentile, so on average we're going to see his sons be in the 34th percentile or the 45th percentile. No, absolutely not. They're just going to be in a lower percentile relative to Michael Jordan on average. If Michael Jordan's in the 85th percentile, on average his sons are going to be in the 77th percentile, 75th percentile. And vice versa, if you have an unusually short father, then on average his sons are going to be in a bit of a higher percentile. If we come here, it says, Figure 5 also shows the regression line for the son's height on father's height. This solid line rises less steeply than the dashed SD line, and it picks off the center of each vertical strip of dots. The average Y value in the strip, for instance, take the fathers who are 72 inches tall. They are 4 inches above average in height. 4 inches is 1.5 standard deviations. The regression line says their sons should be taller than average. So yeah, they're just saying here, if we come, here's father's heights and son's heights. They're just saying that the regression line tries to take care of this, of the regression effect. That's the whole purpose of the regression line being different from the SD line. It's the regression line is taking that into account, whereas the SD line doesn't. Okay, so yeah, with the regression line, it says the overall average height for sons is 69 inches. So the regression estimate for the average height of the sons of a 72-inch man, who's a little bit taller than average, is 1 inch shorter than their father, as opposed to what the point of averages says, that it's 1 inch taller. But this is correct. This is correct from the sense of if you average out the son's heights of 72-inch tall men, it's about 71 inches. That's where the regression line goes. Figure 6 shows the regression effect at its starkest, without the cloud. The dashed SD line rises at a 45-degree angle. The dots show the average height of the sons corresponding to each value of father's height. These dots are the centers of the vertical strips in Figure 5. The dots rise less steeply than the SD line. The regression effect. On the whole, the dots are halfway between the SD line and the horizontal line through the point of averages. That is because the correlation coefficient is 1/2. Each one standard deviation increase in father's height is accompanied by a half standard deviation increase in son's height, not a 1 standard deviation increase. The solid regression line goes up at the 1/2 to 1 rate and tracks the graph of averages quite well indeed. Yeah, so this is just, without the cloud, you can see the regression effect. The regression effect is just seeing how less steeply inclined, the regression effect, at least for the perspective of the football-shaped cloud, is indicated by how less steeply inclined the regression line is. So it's always, since R is 0.5 in this case, the regression line is always half the distance from this horizontal line to the SD line. And this is for the case of the X is the input, Y is the output. If you had Y as the input, X is the output, we would be doing the same thing with a vertical line, and there would be a pull towards a gravitational pull of the data away from the SD line towards the vertical line. At first glance, the scatter diagram in Figure 5 is rather chaotic. it was a stroke of genius. So they're talking about this diagram over here. It was a stroke of genius on Galton's part to see a straight line in the chaos. Since Galton's time, many other investigators have found that the average in their scatter diagrams followed straight lines too. That is why the regression line is so useful. Yeah, for a football-shaped cloud, elliptical-shaped cloud, or pure circular cloud, the regression line is very useful. But now just remember, there's different methods for using that scatter around the SD line to come up with a line for mapping out the points of averages. One of those is the least squares method, and we'll learn that in the 2 chapters from now. But the regression method, the fundamental regression method is a simple look. Multiply the slope of the SD line by R. But with least squares, you're coming to you're doing like a hypothetical line to start with and trying to minimize these distances, the squares of these distances, which doesn't directly use the correlation coefficient in and of itself, but it's still considered. A lot of people call it, some people don't call it regression because of that reason, but it's also called, some people do call it regression because you're still using this scatter around this level of scatter. These distances do in some sense correspond to the level of scatter around the SD line. So it's like these distances here are still indirectly a function of the correlation coefficient. So it's still, some people do still call least squares, they call it regression. Okay, now a look behind the scenes. The regression effect can be understood a little better in some cases. For instance, in the context of a repeated IQ test. The basic fact is that the 2 scores are apt to be different. The difference can be explained in terms of chance variability. Each person may be lucky or unlucky on the first test, but if the scores on the first test is very high, that suggests the person was lucky on that occasion, implying that the score on the second test will probably be lower. You wouldn't say he scored very high, must have had bad luck on that day. On the other hand, if the score in the first test was very low, the person was probably unlucky to some extent on that occasion and will do better next time. Yeah, so in the Michael Jordan example, a regression fallacy would be saying that, oh, wow, look, so on average, we see at the point of averages, sons are 1 inch taller than their fathers. Now, you look at Michael Jordan's sons, and on average, they're all, one is 6'7", let's say, but on average, they're all 3 inches shorter, and you're saying, oh wow, this must have been something about the nutrition that tall people give to their kids. No, it's the regression effect. The reason is because we go and walk in New York City in the middle of the day, and we see what the average height of men is, American men, or if you want to be more specific, African American grown adult men. You see what the average height is. That's the reason. Now, if you want to try and explain why it is that on average we see if you want to try and explain why is it that sons or that combination of sons are only 1 inch taller on average than their fathers, and why the average in general is like 5'9", 5'10", then okay. But don't try and come up with some reason why there's, these unusually tall fathers have shorter sons. Well, no, the reason is because it's the regression effect. Okay, so now they give another example of the regression effect here, and this is going to make intuitive sense as well. So it says, here's a crude model for the test-retest situation, which brings the explanation into sharper focus. The basic equation is, so the observed test score is equal to the true test score plus chance error. So what they're saying by your true test score is that if you are on average, like you're close to the average, like if the average for a class, the teacher designs the test to where the average is going to be an 85% B, and you're always like an 88 B, and you got a 93 on one test. Okay, well, they're saying that your true score is an 88. That's what kind of student you are. But you got a 93 because of chance error. You happen to you don't always study everything thoroughly. all the things that you're supposed to study. You don't study everything. You got lucky, and some of the things you happen to study on this test were there, or you guessed right on some on some of these questions where sometimes you don't guess right. That's the chance error. But your true score was an 88. Now, it doesn't mean that there aren't students that they get a 93 in the test, and that was low for them. They're a 97 student, so they do higher on the next test. No, but it's how hard did the teacher design the test? She always designs it to where it's an 85. That was the average, right? So that's where the gravitational, it's going to be on average, the students in the higher percentile are going to drop. On average. So assume that the distribution of true scores in the population follows the normal curve with an average of 100 and a standard deviation of 15. Suppose, too, that the chance error is as likely to be positive and negative and tends to be about 5 points in size. Someone who has a true score of 135 is just as likely to score 130 as 140. Yeah, so the chance error is on average about 5 points. So it says, of course, the chance error could be plus or minus 4, plus or minus 6, and so forth, whatever. And it's going to be, chance error is going to be symmetric because that's the whole idea. It's purely chance error. It's going to be symmetric. Okay, and so what they're saying is that so it says take people who scored 140 on the first test. There are two alternative explanations for this observed score. Their true score could have been a 135 or a 145. Their observed score was 140, but with the chance error, the true score could have been either 135 or 145. However, the first explanation is more likely because it's closer to the average. There's that gravitational pull. Yes, the observed score, you could have a student that's an exceptional student that their true score was closer to 145, but on average, because look, all the data points are here, on average, the true score is going to be a little bit lower. Michael Jordan's sons, you could have an exceptional case where you have one of Michael Jordan's sons is just as athletic and tall as him. He's 6'8", but on average, because men are 5'9", 5'10", the chances of what I guess the true height is, you could say, is a little bit shorter than Michael Jordan because he's unusually tall to begin with relative to the average. Okay, so the model accounts for the regression effect. If someone scores above average on the first test, the true score is probably a bit lower than the observed score. If the person takes the test again, we predict the second score will be a bit lower than the first score. On the other hand, if a person scores below average on the first test, we estimate that the true score is a bit higher than the observed score. And our prediction for the second test will be a bit higher than the first score. So, okay. Let's take a look at these exercises real quick. As part of their training, Air Force pilots make 2 practice landings with instructors and are rated on performance. The instructors discuss the ratings with pilots after each landing. Statistical analysis shows that pilots who make poor landings the first time tend to do better the second time. Conversely, pilots who make good landings the first time tend to do worse the second time in terms of percentile. The conclusion, criticism helps the pilots while praise makes them do worse. As a result, instructors were ordered to criticize all landings, good or bad. Was this warranted by the facts? Answer yes or no and explain briefly. So yeah, I do want to point out again that you might look at some football-shaped data and you're just looking at the pure numbers based on the units of the data and you're thinking, I don't see the regression effect. Look at it from a percentile perspective. If you have the averages and the standard deviations of the input variable and the output variable are really different, it might be harder to see the regression effect. You look at it from a percentile standpoint and you'll see it. But in some cases, you still might be able to see it just looking at the actual units of the data, like in terms of the test score or the IQ points. But you'll 100% see it when you look at for a football-shaped cloud, when you look at it from the perspective of the percentile. So, okay, but the answer to this question is no, this is not warranted. This is the regression fallacy. If this is an elliptical-shaped cloud, then on average, you're going to see the pilots that did well the first time are not going to do quite as well the second time. This is a characteristic of any football-shaped cloud, so you can't make any inferences, like actual inferences about the data from this. And if you're tempted to think, well, why not? That's a characteristic of it's football-shaped data. So all of that kind of data has that characteristic. Okay, well then that would be like saying that, oh, it was Michael Jordan. It's tall people. Unusually tall people have different. They give their kids different nutrition than not as unusually tall people. It doesn't make any sense. It's just a pull towards the average, or any conclusion about why a tall people on average have shorter, a little bit shorter sons. Oh, it's the nutrition, it's the environment they're brought up in. No. Okay, an instructor standardizes her midterm and final each semester, so the class average is 50 and the standard deviation is 10 on both sides. The correlation between the tests is around 0.5. One semester, she took all the students who scored below 30 at the midterm and gave them special tutoring. They all scored above 50 on the final. Can this be explained by the regression effect? Answer yes or no and explain briefly. Okay, so the class average was 50 and the standard deviation was 10 on both tests. Okay, and so she tutored that's between the midterm and the final. So she tutored students who scored below 30 at the midterm and gave them special tutoring, and they all scored above 50. So on average, they scored above 50. Well, no, that's not the regression effect. They started off a good bit below average. Well, the average is 50 on the midterm, and then they all improved to better than the actual point of averages. No, that's not the regression effect. That would be like if you had Michael Jordan at 77 inches tall, and all of his sons ended up, if the average height is 70 inches, 5'10" of men, and all of Michael Jordan's sons on average were 65 inches tall, like 5'5". Well, no, now that's different. That's different. You don't expect, the regression effect is not saying that if you're in a high percentile, the 85th percentile on the incoming variable, that on average you're going to be below the 50th percentile on the second variable. No. And so this is different. There is something you could look into here about the phenomena itself. Okay, in the data set of figures 5 and 6, are the sons of the 61-inch fathers taller on the average than the sons of the 62-inch fathers, or shorter? What is the explanation? Okay, so are the sons of the 61-inch fathers taller or shorter than the sons of the 62-inch fathers on average? Okay, well, it looks like the sons of the 61-inch fathers are a little bit taller on average. You've got some points out here. So what's the reason for this? Well, this is just chance variation. We would expect if there was a lot of data points, then because of the slope of the regression line, on average, we would expect sons of 61-inch fathers to be a little bit shorter than sons of 62-inch fathers, right? Because that's what the point of averages tells us. And thus, that's what the slope of the regression line is telling us. In general, you're going to have, on average, a son is going to be a little bit taller than the father. On average. Here, this might be confusing to you because we said, well, wait, Michael Jordan's sons were on average 3 inches shorter. That's true. But here we're comparing one father to another father. If we're saying that, like, okay, if you had like Shaquille O'Neal's sons, on average are going to be like 4 inches shorter than Shaquille O'Neal. But on average, Shaquille O'Neal's sons should be a little bit taller than Michael Jordan's sons because of the genetics, right? Because Shaq's taller than Michael Jordan, right? And same here. A 61-inch father, on average, compared to a 62-inch father, the 62-inch father is going to have a little bit taller sons. But why don't we see that here? Because of chance variation. There's not a lot of data points. If there were a lot more data points, we would then expect to see, okay, the sons of this father are going to be a little bit taller on average than the 61-inch father.